Okay, let's jump right into it. Today we'll be talking about clustering. We'll do a very quick review of like supervised versus unsupervised learning. And for clustering, we're going to go over two main clustering algorithms, K-means clustering and hierarchical agglomerative clustering, which I will call HAC. So as a quick overview, we went over a lot of this yesterday, but supervised versus unsupervised learning. In supervised learning, the system is trying to learn from previous examples, whereas in unsupervised learning, the system is trying to find patterns directly from examples given. A quick way to decide if something is supervised or unsupervised is to see if it's labeled on what you want to predict for. So if data set is labeled, it's usually supervised. If it's unlabeled, it is unsupervised. So here you can see in supervised, this I guess is like a decision boundary that's created. I don't know why this image is so small. And in unsupervised learning, we're just going to group our data based on patterns that we find in their features. So before we get into the types of clustering, the overall main idea of clustering is to try and divide our data into groups, into clusters. In plain words, the aim is to segregate groups with similar traits and assign them into their clusters. More overview, two kinds of clustering, hard clustering and soft clustering. The two methods we're going to talk about today are hard clustering methods, but you can actually find in K-means clustering, you can actually find the probabilities of being in clusters that will be soft clustering. So back to the definition, hard clustering, each data object or point belongs to a cluster completely or not. So for example, if you're clustering New York City locations, a location can only be in a single borough. It cannot belong to multiple. It can't have like 1/3 in this borough, 2/3 in another. Whereas in soft clustering, you can actually get these probability measures. If you have like 5 clusters, you have a single data point, you can potentially get, the probability of a point belonging to each cluster. That's the main difference between hard and soft clustering. The two that we're going to talk about today, we're going to talk about them in context of hard clustering, but again, K-means you can actually pull out the probabilities and get their soft clustering. There are a lot of different kinds of clustering algorithms. These are two of, I think there are 4 main ones. I honestly forget the name off the top of my head. But the 2 main kinds of clustering algorithms, and we're going to be talking about one from each. So first, there's centroid-based clustering, where clusters are represented by a central vector or a centroid. And we'll get into like what that looks like in a little bit. And the centroid doesn't have to be a member of the data set. The centroid is just what determines or what a cluster is. It's an attribute of the cluster, basically. What's the center of the cluster? And K-means comes under a centroid-based clustering algorithm, and we'll see why in a little bit. Next, there is connectivity-based clustering. That's what HAC is. HAC is a connectivity-based clustering method. And the main idea behind this is you're going to connect points in data space. We'll actually get through all of this later, so I won't go through this right now. Questions about like the intro and definition so far? Awesome. So here you can see some of the new ones that we're importing. We have scikit-learn has a cluster sublibrary where we're getting K-means from. And in the same place, if I actually scroll down to, I think here, HAC, you have agglomerative clustering from the same cluster sublibrary. All right, so let's start with K-means clustering. This looks, I feel like whenever you see math equations, it seems kind of intimidating, but it's really not. I have the documentation here that I'll look into later. But the whole idea of K-means clustering is you actually first have to tell it how many clusters you want. So after you've decided how many clusters you want, the algorithm is going to randomly pick points to be the starting point. You can also tell the algorithm what you want your starting points to be, but those starting points are going to be your centroids, which is what I mentioned earlier. So I'll also refresh these, and hopefully we can look into see what those are all about. But first, you're going to choose starting points. And then with the starting points, you're going to see with each starting point and which, okay, actually, let's do this. Let me see if I can get this to work. So you're going to choose a starting point first. Please load. There we go. And what's happening here is basically for every other point that isn't a starting point. So these 4 points here are our starting points. For every other point that isn't a starting point, you're going to figure out, all right, which is the closest to a centroid? And then you're going to recenter your centroids. I don't know if that makes sense. I'm going to refresh this once it's done. All right, so these green points are the starting points. For every other point, they're going to see, all right, which is the closest centroid? And form these clusters first. When all the points have been connected, the centroids recenter to everything that's the closest, and then they recalculate the distance between each point in the centroids. So what happens is at the end, you form clusters like this. I feel like the diagram, I don't know, I find the diagram kind of easy to understand, but does anyone have any questions about this process?
Excuse me, Ish. Every black points in this picture is one row in data frame?
That's right. Every black point is one row in the data frame. And even the green points that it started as is also a point in the data frame. And then only after we're done making the connections between points and centroids, the centroids then readjust to the new average. So each of these green points is the mathematical average of everything connected to it. And then this green point is an attribute of the cluster. Any other clarifying questions about this process? All right. So because this is the process, and let me just run this and go through some of this first. For measuring the distances, typically the Manhattan distance is taken. So it's literally just the absolute distance between each argument of the coordinates. So pretty easy computation. And then you're updating this cluster centroids by literally taking the mathematical average of each argument of the coordinates. And then as you saw in the GIF earlier, the centroids will just readjust. And when the algorithm no longer has to update centroids, then your clustering is done. So several pros and cons. So each of these are actually different GIFs. So we're looking at this one, and these are the clusters that result from it. Let's take a look at this example. This is just the same data set, but with different starting points. So hopefully this will run. So here we're starting on the right-hand side. And because it started on the right-hand side, and this point is an outlier over here, none of the points will see this centroid to be its closest. And so because of that, as it readjusts, and I think at the very end, you end up seeing that this point is a cluster on its own. So this basically goes to show that the starting points of your clusters can really affect your clustering results, often with K-means clustering. And we'll take a look at the documentation a little bit. Often with K-means clustering, you do end up running your clustering algorithm a couple times. Maybe you want to clean up your outliers if you have results that look like this. But usually you end up running the same algorithm a couple times because it is very random. Or introduce a random state. But if you have a random state and you have this point over here, it's going to keep being that point over there. Questions about this? So these are just 4 separate examples of clustering with points starting at different, the centroid starting at different parts. So here it started on the left, here it started on the right. These are examples where it started on the top and bottom. You can see that they are kind of similar, but they are different.
Can I get a clarifying question again? So
absolutely.
The starting points are data points, but then as they move, they actually move. So they don't exist as data points anymore?
That's right. That's right. As the centroids update, they likely won't be a data point because it updates to become the center of the cluster. It just needs a starting point. But as it updates, it doesn't have to be represented by a data point. Cool. If you're curious, feel free to take a look at these GIFs on your own. All right. Any questions before we move on? Cool. So K-means is a fairly, I would say one of the simpler algorithms. So let's just take a look at how we use it. This data set is not this data set, but actually, I think it is this data set. Anyways, here I have imported the data at the start. It's just, I don't even know what this data is, but it's a 2-dimensional data set so it's easy for us to visualize. Here, I'm just displaying, this is what the data set looks like. This is a dot describe. You can see that there are 3,000 data points here, and it's pretty normally distributed, I would say. What I'm doing here now is I am instantiating my K-means. And let's take a look at this. With K-means clustering, usually you only have to adjust the number of clusters, which is something that you get to decide. And this part is what I wanted to talk about. Here. So deciding on the starting points, I actually just saw a question from Tim. The data points that it starts at are arbitrary. In scikit-learn's K-means algorithm, it has a way of deciding what are the best starting points to start with. I honestly have not looked into how this is determined, but it has some algorithm for figuring out what are the best centroids to start with, and that's their K-means ++ initializing algorithm. So there's that, or you can tell it to start, you can give it an array and you can tell it to start at a certain point if you'd like. But most of the time, if you don't have an inkling of how you want your clusters to look, you just let the K-means algorithm figure it out for you. So it works in a very, very similar way to actually PCA and all of the models with scikit-learn that we've worked with. We instantiate it, and when we instantiate it, this is a hyperparameter, the number of clusters. And then when we fit it, you can see this is the usual that we get. And after it's fit, as I mentioned, cluster centers is it's an attribute. So you can just pull out the cluster centers from here. Other than that, figuring out which cluster each point is, you use the dot predict. So here you can see there is the dot predict. There are also several other methods within K-means that I think are good to know. So here we have our usual, we have our fit. We have our predict, which are the same ones that we've been using in models. We also have fit predicts, which I'll actually go through later. It's basically like how we were doing fit transform with a scalar. Sometimes for clustering, because we can do the fitting and predicting in one step, that's a method that you can use as well. And I do have an example of using that method later on. All right, so what we do here, dot predict, as you know, returns an array of results. And you can see here, I have 4 different clusters. Let's actually take a look and see. Let's turn this into a series. I hope this is a run notebook. I forget if it is. Let me just run it real quick. All right, yeah, this notebook is not run. So let's run this. We can see our cluster centers, our dot predict. You can see that the numbers actually changed. The cluster results should be similar, but you end up having to manually label your clusters later anyway, so the numbers don't really mean anything. It just tells you which group it belongs to. So really quickly, let's take a look and turn this into a series. All right, so this is a series now, and let's do a quick value counts. There we go. So you see that with this particular K-means clustering, it has put 952 of our 3,000 data points into cluster number 2, about 900 in 0, and roughly 600 in 1 and 3. And so our task after the machine has done its work here is to look into the data points, and maybe you want to manually give these cluster groups like a name that represents what the cluster is. So because we get an array from this, I turned it to a series, and all I did was attach it to the original data frame. And oh yeah, we have our data count, our value counts over here, and we can also visualize our clustering results. So really quickly, this I think was a very similar data frame as that, but yeah, these are our clustering results. You can see that is pretty well defined. You have some pretty clear boundaries between the points, but these are our clustering results so far. Any questions? All right, so actually, since we have, I think we will have time to do this. If I were to turn this into 6 clusters and run this, you see I now have 6 cluster centers. This is what my new number of points in each cluster is. We rerun this real quick. You see, this is what our clusters looks like. So yeah. Questions before we move on to how do you figure out what your best number of k is?
So this is just 2-dimensional data, right? This is not a whole bunch of variables.
That's right. This is only, yeah, it works in the exact same way. All your data has to be numerical to work with clustering. So do your like one-hot encoding, your dummy variables, get rid of your strings before you do clustering. But yeah, it works in the exact same way. Actually, this would be a really neat way to use PCA if you end up doing clustering on something with like 10 plus columns, or actually even more. You can get your clustering results, get this, run PCA on your features, and then you'll be able to visualize what they look like in like 2 or 3-dimensional space. So that is a use case of PCA with clustering, and it's really to help visualize and show what your clusters look like. All right, so finding the best K, I'm going to talk about a couple methods, but before getting to that, I also wanted to say that the number of clusters that is best for your project or your situation is really dependent on context. So the same example I talked about yesterday with like clustering basketball players, I actually did have a student do a capstone project on exactly that. Like, are there better ways to group and classify basketball players other than their like positions that they play? And he was like, I use all these methods, and it told me that my best number of clusters is like a throw up between like 3 or 7. And he was like, I'm not sure which one to pick. And I just asked him right back, which one makes sense to you? Does it make sense to have 7 groups of players or 3 groups of players? I don't know sports that well, but I think he decided on 3 main groups of players. So it's really, really subjective. It is up to you to decide what the best number of clusters are if these like mathematical methods are, giving you different answers. So I'm going to be talking about 2 of the main methods, the WSS elbow method and then the silhouette score. So the first one, WSS elbow method, WSS stands for within cluster sum of squares, not to be confused with like the RSS, what was the other like total sum of squares that we're talking about with linear regression. But this is the within cluster sum of squares, which basically measures the distance between the centroid and every point in its cluster, just to see how compact clusters are. And you can imagine if you have more compact clusters like 1, 2, 3, better results than if you had like weird, I don't know, I can't even imagine, but like if they give you clustering results that work all over the place. So the idea behind these partitioning methods, and Kmeans is a partitioning method, is to define clusters such that the intra-cluster variation is minimized. You can imagine you want your clusters to be compact. So WSS is small. And yeah, we want it to be as small as possible. So the elbow method looks at the total WSS as a function of the number of clusters. And you should choose a number of clusters so that adding another cluster doesn't improve the total WSS by much. You can imagine if you keep increasing the number of clusters that you have, your blobs are going to get smaller and smaller in space, and your WSS is going to keep getting better. So the idea is to figure out where is it such that as you increase the number of clusters, the marginal decrease in your WSS is not as much. So WSS from Kmeans is easy to get. Kmeans has an inertia variable, attribute, sorry. So if you scroll down and take a look and see, do they have it in here? I guess not in this one, but Kmeans has inertia, and inertia is literally WSS. So you can use inertia to get your WSS scores. So I'm basically running my k-means for 2 to 9 clusters. And we plot what is called an elbow curve. It's literally called an elbow curve because it looks like an elbow, but you can also call it the WSS curve. But usually what you want to do, it doesn't always look this clean, but there's usually a point where your WSS decreases by a lot and then starts to plateau off. And then you choose this point to be your best number of clusters. And that's because you can see from 2 to 3, the WSS decreases by a lot. But then from 3 to 9, you can actually see there are slight kinks in the curve down here. But overall, the marginal decrease in WSS is not as much. So you want to keep at 3. You can see that there's a slight kink, I believe at like, I can't even see these straight lines, but imagine that there's another kink at 6. That could be another point of contention, another like number of clusters that you might want to consider. But again, really depends on your context. But usually wherever you see a kink in the line is a good indication of, all right, this number of clusters is much better than our previous number of clusters, if that makes sense. But yeah, you can see the WSS is consistently decreasing just because the more clusters you have, the smaller your blobs are. So yeah, you look for the elbow where the marginal decrease in WSS is subsequently reduced. And based on this graph, the best K is 3. So obviously with these blobs, 4, 5, 6 wouldn't have really made sense. You can sort of see visually in this example. But if I were to change my n clusters to 3, you'll see clearer blobs. There we go. 1, 2, 3. And that does make sense visually looking at our data. Questions about this so far?
Yeah, quick question. I may have just missed this. When it finds the center of a cluster, is that center a data point or will it just be an arbitrary center?
It's an arbitrary center. It is the average of all the data points in the cluster.
Okay, great.
Awesome.
And a second part to that, is there any merit to reducing your cluster to 1 and then just finding the center of all of your data? Does that ever come in use?
Ooh, that's a good, like you mean like with all of this, finding
Yeah, if for some reason you wanted to find the exact center, would that be the way you would do it?
You could. Honestly, the center is literally like the mean of every feature. So may or may not come in handy. Maybe you want like an overall measure of like, all right, what is the most average point in our data set? That could be useful. In terms of clustering, I'm not sure because usually like the point that's in the center would be the hardest one to cluster. But yeah, that's interesting to think about. I can imagine some usages of like finding out what your center point is, just so you can, compare other data points to it. I feel like points that are around the center make for good test points in clustering, just to see like how they would cluster these kind of ambiguous points. Like imagine like these two guys in the middle here. You could argue that, this blue guy maybe would be better here. I mean, based on the data. If there was some context to this data set, you could maybe say that, all right, maybe this guy belongs there. Maybe this guy belongs here. The points that are in the middle are typically more ambiguous to cluster. So could be something that you do like as a post-clustering analysis, which is also something that people do.
I have another basic question. So this can be done supervised or unsupervised, or this looks like it's unsupervised to me?
Yeah, this is 100% an unsupervised algorithm, just because, you cannot scientifically validate that this guy should have been in this cluster. There is no like false, like it's hard to say like what's true or false in a clustering problem because you don't have these defined labels. Sometimes what people do, and definitely look into these if you want to incorporate clustering into your projects for phase 4 capstone, some people actually first do clustering to create some labels and then predict on those clustered labels. That's something that's pretty common, especially for like if you have a data set that is very interesting to you but unlabeled. One step is to first do your clustering, and then you can use the clustering results as your labels. But clustering in itself is unsupervised. Anything else? All right, so we talked about the WSS elbow method. The other one that's very commonly used, and there are actually a lot of different ways to evaluate your cluster. I believe one of your lessons in clustering actually goes through like 4 or 5 different measures that are built into scikit-learn. But I would say that the elbow method and silhouette coefficient are the most common ones. So silhouette coefficient is, to start, the average silhouette approach, and that's the approach that gets you to the silhouette coefficient, measures the quality of clusters by how well each object lies within its cluster by estimating average distance between clusters. So I realize that that is kind of an ambiguous sentence. So in more detail, each data point has a silhouette value. And it is a measure of how similar one data point is to its own cluster compared to other clusters. So what it does is, let me see if I have an explanation here. All right, so basically what it does is it measures it takes the one data point, measures its relative distance to its own cluster versus other clusters, and you end up with some silhouette coefficient. And what you want to do is with each cluster, you average the silhouette values for all the data points in each cluster to form your average silhouette for across all the clusters. So yeah, you want to have a higher value for silhouette coefficient, and you'll see here that is actually built into scikit-learn, so you don't have to worry about the calculation. If you see low or negative values, the clustering configuration might have too many or too few clusters, usually too many. And also silhouette score can be calculated with any distance metric. I think by default it is Euclidean distance, but let's take a look and see what this does. Again, the same range of clusters, same data set. We're going to look at the silhouette scores for clusters between 2 to 9 clusters, and we get our silhouette coefficient here. You can see here that we have metrics.silhouette score, where you have your data and your cluster labels. So it does that automatically for you. And then we're appending that score and plotting it out. The dotted line across is the average, but you can see that there's an obvious peak at k equals to 3. Questions about this? I will say these methods are used for if you don't have an idea of how many clusters make sense. So there are some problems where you want like 4 or 5 groups, for example, then you'll just straight up just use 4 or 5 as the number of clusters in your model, and you wouldn't even worry about it. But if you want to do a clustering problem and you're not sure how many groups make sense, you would use these methods to verify. All right. This is the end of K-means. Before we move on to the next one, any questions? Here I have a pretty good reading that talks about like data sets that don't work very well with K-means. I would say like it is good to keep in the back of your mind, but it's a good read. I don't want to go through it right now, but it's pretty self-explanatory. They have a lot of examples in there. All right, so the next clustering algorithm that we're going to talk about is hierarchical agglomerative clustering, AJC. And I'm just going to open the documentation just so we have it. And how it works is kind of the opposite of K-means. Hierarchical clustering sets out to group the most similar 2 observations together from a bottom-up level. So K-means is not exactly top-down, but in these GIFs that we saw at the very start, let me just refresh this. Why does it keep doing that? Let's see if this refreshes. All right, never mind. You can see that with K-means, and let me just pull it up again. With K-means, it started by associating every single point to a cluster, and then just continuously adjust the cluster centroids. So you can see here, every data point is going to be associated with a cluster at the start, and just makes adjustments as it goes along. HAC does not do that. HAC, and let me just keep this here and go down to HAC. So HAC starts with each observation being its own cluster. So it's kind of a bottom-up approach compared to that other one is kind of top-down, but not really, but this is definitely a bottom-up approach. Every observation starts out as its own cluster. And then what it's doing, it's going to look for similar clusters. So the most similar pairs of observations would form a cluster. And then the next most similar groups will fuse together, and we continue this pattern until you have one big cluster. So what you have is like, you actually end up with a tree-like diagram called a dendrogram. And I'll have examples of dendrograms in a bit, which allows us to view clusters obtained for each possible number of clusters from 1 to n being the number of points in your data set. And then all you have to do is just decide where to cut off the dendrogram to define your clusters. Before I go into like versus k-means, I like this a lot. This is code that I got from that page there, so not mine, but it creates this diagram that's pretty cool. And I think this illustrates really well how HAC works. So starting off initialization, each point is its own cluster, and it looks for which 2 points are most similar to each other first. And you can see at step 1, it's defined that, all right, these 2 points are most similar to each other. Let's make those 2 points into one cluster. So you end up with one less cluster in total. And then next you'll see, all right, the next 2 most similar are here, followed by these 2 over here, followed by these 2 down here. After it's been formed, you can actually connect individual points with clusters as well. It's really just average distance between clusters. So you can see here, you initially have pairs, but then after pairs, they find that the next most similar thing is actually this third point to be grouped here. So it's just going to keep looking for similarities between clusters, and you're going to eventually end up with one big group. So if we actually continue this, I think a couple more steps, it'll probably like maybe fuse these 2 together and then fuse the whole thing to create one cluster. And basically how you get to like your specific number of clusters, you just cut it off at some point. So here would be your result if you had 3 clusters. If you want 4 clusters, this would be your result. If you have 5, this would be your result. So HAC, a very bottom-up method. Something to think about is that HAC is not random. It is completely distance or similarity based. So no matter how many times you rerun it, it'll give you the exact same results unless you have different data points. But yes, any questions about like the intuition and how HAC works? All right, awesome. So versus k-means. The goal of k-means clustering was to assign observations to a pre-specified number of clusters according to the distance between centroids and observations. So again, k-means at the very start, every point is already assigned to however many number of clusters that you've determined. And that can be a disadvantage. You have to specify the number of clusters beforehand. Therefore, we don't have to do this with HAC. Really quickly, pros and cons of HAC. It is pretty intuitive and easy to implement. It is, I would say this is subjective, but it's typically more informative because it takes individual relationships into consideration rather than associating a data point with some centroid. And also again, we'll look at dendrograms, but in smaller data sets, you can actually see the dendrograms and determine what the best number of clusters is based on your data points. Disadvantages, it is quite sensitive to outliers. And also because of the way the clusters are being merged, you can't undo a merge. So let's say you have an outlier and you happen to merge this outlier one way, the distance between that cluster and every other cluster can be skewed by that. And we'll get into that more with like the kinds of HAC. But any questions before we move on? All right, so the types of HAC and how they differ is basically how they determine similarities between clusters. So between points, yeah, pretty simple. You literally find like the distance between points. But once they've combined here, what would you use to represent this combination of points in this new cluster that's formed? And that's where the different types of HAC come into play. And there are 3 main types, and this is also something that you can tune in your as one of your hyperparameters. So here you can see the number of clusters, same as k-means here. And then you have your linkages, and we'll talk about what each linkage is, but you have all your different kinds of linkages here. which basically determines how you decide on the similarity between clusters. All right, so there are three main types of linkages that are used. So first, single linkages. So how you determine how similar clusters are. Between any two clusters, you're going to look for the minimum pairwise distance. And it's going to be pairwise distance between individual points. So the distance between these two clusters is determined by the distance between the points that are closest to each other. So it's literally just this guy here, and this will be the distance. So that's a single linkage. It just takes the closest distance. And let's say there was like a third cluster, and let me annotate this. Let's say that there was a third cluster over here. And let's make some bigger dots. All right, let's say there's a third cluster here. If we want to find the distance between this cluster and this cluster over here, it would be determined by the 2 points that are closest to each other. So for this case, we're using this point here. For this case, whoa, that was big arrow. For this case, it'll be probably this distance here, or actually maybe this distance here, whichever one is shorter. So for differences between different clusters, it can be different points that are being used to gauge the distance. Does that make sense? All right. The next kind of HAC is a complete linkage, which is determined by the furthest distance. So opposite of this, we'll just look for the furthest distance between clusters, but yet we want to group them by the shortest distance relative to other clusters. So the linkage is determined by the maximum distance between clusters. And then finally, average linkage. It'll just average out all the distances between each of the data points. And it'll do an average of like 1 point to every other point. So this is something that I will say is pretty difficult to tune. I would say just pick one and go with it. Or if you wanted to see the results of different ones, and if you know your data set very well, you can make more informed decisions on which linkage you want to use in your clustering problem. All right, now for dendrograms. I'm not going to run this code because it does take a little while. As you can see, you can't read anything on this graph. I have a smaller example that I'll show. So I would only print dendrograms. Think of it as like your decision trees, where it doesn't make sense to print after like, I don't know, a depth of like 4, because it becomes very hard to read. But this is what a dendrogram is. It basically shows you your entire tree of clustering. So at the very bottom layer here, and I actually did a truncated version here that's not as clear. That's not as clear as I wanted it to be. But imagine at the very, very bottom layer, you have an entry for every single data point that existed in your data set. And then it literally shows how the clusters are being formed. And so you can see like maybe from about here, this cluster here links with this cluster here, more linkages are happening. You're ending up with 2 big clusters, one on either end here, and they link to the top here. So dendrograms, it is really in the back end, it shows how the clustering is, how the clusters are being formed. But again, with a lot of data points, it doesn't really make sense to look at. Here you can see I truncated it to show like the last 4 clusters. So here you can see that, and this is 2,997 of my points were all in one cluster, and we had apparently 3 outliers over here. This is how the clustering happened. And then it grouped these 2 together, followed by this 2 with these almost 3,000 points, and then this point at the end. So this really shows how the clustering is happening. It really shows like the story of your clustering. All right, now to just quickly implement this, I'm importing agglomerative clustering. I'm going to use n clusters equals to 4 and do a fit predict on my data. Oh, sorry, this is Kmeans. I just wanted to compare, but I just wanted to show that fit predict because you don't usually have to fit and then predict for clustering, because this again will give you your cluster results. So what I'm doing here is I'm doing a fit predict on my data set, doing the same thing on my data set with HAC. And you can see I have my results here. Again, the numbers don't really matter. It's up to you to label them on your own. But to compare the clustering results, this is Kmeans and this is HAC. you end up with it looking slightly different. Overall, kind of similar because you still have like, this one is its own thing. The pink one is its own thing here. It's just like these two are a little bit different. But yeah, if you know your data set well enough, you maybe have a little bit more of an intuition to decide like which cluster is better. Maybe take a look and see like, which are the points that were given different clustering results between the two, and you can decide which one makes more sense in your context. So another thing I wanted to show you all is basically the hierarchical nature of it all. If I were to increase the number of clusters of HAC, all you're doing is you're splitting your clusters up. So here I have a bunch of subplots increasing the number of clusters 5, 6, 7, and 8. Let me just zoom out a little bit. So with 5, 6, 7, and 8 clusters, you can see that as we get more and more clusters, all we're doing is we're splitting existing clusters because that's the hierarchical nature of it. It's doing it bottom up. So you can see from 5 to 6, we're only just splitting up this cluster here, this dark blue one, into 2 here. To get to 7, it decides to split these two up. And to get to 8, it's splitting the dark blue here into the gray and the light blue here. I should have said it the other way around. It really is merging it together rather than splitting it up. But yeah, that goes to show that HAC, the whole tree is built when you run an HAC model. Is just where you cut it off that determines your number of clusters. Questions about this so far? All right. Again, with HAC, you can use the same metrics as we did for Kmeans. Unfortunately, I don't have this here because I don't have elbow curve here because elbow curve is not built into HAC for some reason, but silhouette score is. So you can see, let me just zoom back in. For HAC, our silhouette score is done here, but not, there's no inertia for HAC like we did have for Kmeans. So that's something to think about. But you can see here for this same data set, it also determined that, yeah, it makes sense to have 3 clusters. Questions before we summarize clustering?
I have a question about the linkages and what are the usage of those?
Yeah, so because HAC, we're trying to determine like, what we're doing is we're grouping similar things together to like basically merge them into clusters, right? So basically like how we get from this initialization to this step is we decided like, all right, which 2 are the closest together? More specifically, to get from like here, or actually no, to get from step 5 to 6, how do we determine that, this point here is the closest to this cluster? The linkage just determines the kind of distance, like how we measure the distance. So using a single linkage, the distance is, and let me see if I can draw this out over here. For single linkage, this will be the distance, the red from that dot to that dot. If we were to use the complete linkage, the distance would be determined by this dot to that dot, the orange one. And then for average linkage, it would be the average of the 2. And same thing for like for these other, is the same thing for all of the merging. So how the tree is formed, how you determine what clusters are most similar to each other, that's when you can tune that's where you use different linkages. That makes sense. Anything else? All right, well, as a really quick summary, Kmeans is centroid based while HAC is connectivity based. I think like understanding how the clusters are formed can help with the intuition sometimes. Like for example, if you know that you want similar objects together, maybe HAC is something that you want to do. Or if you want something that's like more big groups, K-means might make more sense. Again, these are very, very subjective. In a lot of problems, people just choose one and tune the number of clusters because, or like look at the differences between your clustering results between each clustering method to just decide what you want. Another key difference, K-means has an element of randomness, basically what the starting points of the centroids are, while HAC does not. It is always fixed based on distance. And again, in context, you want to examine the data points in each cluster to manually label them. So after clustering, there's usually a lot of other work to be done. So with these clustering results, for example, so let's say I have my 3 clusters. Do I have a 3 cluster example? Let's see. All right, let's say I have these 3 clusters, and this data set is arbitrary, but let's assume that these are like types of irises. Let's just assume this is like the iris data set. Based on these clusters, maybe I want to then subset these irises. Maybe I want to say like, all right, these are like the, again, it also depends on the features. Say that, okay, maybe these are the purple irises. These are the blue irises, and these are the irises that are, I don't know, poisonous or something. And it's really up to you to look into the data points in each cluster. Usually what people do is like another round of EDA on each cluster to see how, like, you know, what patterns are forming within clusters and what is salient within each cluster. And it's up to you to do the manual labeling. And then, yeah, maybe, you know, I have the iris data set that tells me species. I can see how these and species are different, so on and so forth. So like the next steps that you do are quite dependent on the context of your problem, but yeah, clustering, again, very, very useful for creating labels for your data. And also it's a good EDA step, honestly, just to like figure out like what kind of patterns are happening in your data. All right. That is all I had to share about clustering. Does anyone have any questions to round up?
Is there any way that we could understand that we are clustering our data in the wrong way, for example?
Yeah, so clustering, very, very interesting, because for clustering, because they are very distance-based, not so much you can tell that they're wrong or not. You can also adjust you can adjust what features you want to be stronger by scaling your data. It's very, very similar to like K nearest neighbors, where the distance between like your different features does affect your clusters. So if you want to, like, you know, cluster something based on their color more, you could maybe scale those down so that it will be closer in those respects, in those aspects. So yeah, you can do that. Really, I would say if you want to see if your clustering makes sense or not, is honestly to do like a quick EDA per cluster to see if what you have makes sense. Typically you end up seeing, like, if you honestly do, like, let's say you have a result that looks like this, right? If I have my clustering results here, I would actually subset my data frames. I think one quick way to do that, let's see if I can do that right here. Results. Okay, I haven't done pandas in a little while. Results cluster equals to 0. And I do like a quick dot describe. If I do that, and if I do the same thing here, but look at my cluster equal to 1, take a look and see if there are any main differences. So you can see that the mean of cluster 0 is around 9 and 10. The mean here is 69 and -10. And through this kind of EDA, maybe you want to go even deeper, take a look at what the edges of these clusters are. But yeah, this is one quick way to take a look and see what your clusters are looking at. And yes, these will actually be your cluster centers too. So cluster centers, which you can get out from here. Oh yeah, yep, the same numbers here. So it's really up to you. With more context, like if these were actual things, maybe it would make more sense. But that's up to you to figure out in your project if you do decide to do clustering.
Thanks.
You're welcome. Anything else?
Yeah, when do we get our hands on those sweet Flatiron t-shirts?
You actually do get these shirts and you get a hoodie as well when you graduate. So yeah,
Oh,
I
can't
believe
wait.
the current color that is being distributed is a tri-blend gray t-shirt with I believe the lettering is white and then the slashes are blue. Yeah, I believe that's the current one. I don't know. They like rotate colors every so often. So that's something to look forward to. Anything else? Cool. I know I owe you guys working groups. So I will, you know what? I'll get that done right after this. All right. If there's nothing else, and final call for questions, going once, going twice. All right, I will see you all tomorrow for PySpark. PySpark and Docker, that is usually the topic that people skip in this phase just because it requires like a lot of installation outside of Jupyter. You actually will be running Jupyter Notebook within this other thing called Docker. So I will be doing like a very quick overview of like the stuff that you can do within it, some of the more important concepts, but I won't be going through exactly the same stuff that is in the lessons, just because it's pretty much like learning pandas just in a different language. And the setup, if you have issues, let me know, but I will tell you first, I only know how to do it on a Mac computer, and I will outsource all of your questions that you ask me on a Windows to other people. So yeah, just some background before we get into tomorrow. All right, let me see if there's anything. I don't think there's anything else I have for you all. So, all right, I will see you all at your project reviews. Those are going well so far. And if not, at tomorrow's study group. All right, have a good rest of your day, everybody.
Thank you.
Bye.